Welcome to another podcast. In this episode, we're going to be taking a look at our second video involving autonomous differential equations, and we're going to spend most of our time focusing on the stability of critical points in this one. I want to include something called the stability theorem at the end of this video that you should definitely take note of. So we have a differential equation to start off looking at, and we want to find the critical points to begin with. So I'm just going to do a little bit of algebra here. We're going to factor out the y. And hopefully we recognize how to factor this quadratic, which it is a perfect square, it looks like. So we've got y minus 2 squared, which means that our critical points are y equal to 0 and y equal to 2. We only have two critical points here, even though it's a cubic. And so we've got our pictures here of kind of what's going on with the solutions. Let's start with the phase plot. So let's do the phase plane first, or the phase portrait first. Remember, the phase portrait is a graph of y versus y prime. And so for the phase portrait, for this particular graph, we're going to pass through the point 0, and we're going to tangentially touch the point at 2. And so it's going to be pretty steep here. So it's going to look like this. That's a little too steep. Let me back up just a hair on that. So it's going to look like this, touch, and then keep going. All right, so this is the graph of the right-hand side in this case, which is the function y minus 2 squared. So this is what we graphed, and if you remember from last video, what we wanted to look at are each of the regions that are created by the critical points. In this case, to the left of 0, we have y prime is less than 0 over here, so solutions will be decreasing. In between 0 and 2, y prime is greater than 0, and so in this zone, solutions will be increasing. And then finally, to the right of 2, so this is y equal to 2, this is y equal to 0 in here. To the right of 2, we have y prime, once again, is greater than 0, and so solutions are going to be increasing again. Let's draw in the phase line. So the phase line for this particular equation, we're only going to have 2 points. We're going to have y equal to 0 and y equal to 2. And what you notice is we have a little bit of a different behavior here. Below 0, it decreases. That's fine. Above 0, it's increasing. This is going to make 0 unstable. But here's the new behavior. If you watched the last video, we only had stable and unstable. Here, we've got increasing below 2, and it's still increasing after 2. So this is neither stable nor unstable. It's what we call semi-stable. So this is a semi-stable critical point. All right, what does that mean for the picture of solutions? Well, I'm only going to have 2 critical points, one at y equal to 0 and then one at y equal to 2. So let me draw those horizontal lines in. So there's y equal to 2 and then y equal to 0. And in between these two, we are increasing up to 2. Above 2, we're also increasing. And those shouldn't be curled at the end. It's just the graph is, or the pen tool I'm using is making that happen. But it should just be straight exponential solutions above 2 that are increasing. And below 0, we are decreasing. So this is a little bit of a different picture, especially with the stability or the semi-stability at y equal to 2. The picture is going to look a little bit different than it does for stable or unstable. Now, the question is, how do we know that a given critical point is going to be stable or unstable? So, for example, the question I'm asking here is, what determines the stability of a critical point? And what I'm about to list is something called the stability theorem. So this is the stability theorem. It's not going to be the last time I refer to this semester. So here's how the theorem starts out. I want to let y equal y0, or y naught, be a critical point for the function y, or for the differential equation, excuse me, y prime equals f of y. Then there's three possibilities, which we've seen in these videos. The first possibility is y naught is stable. And when does that happen? Well, I didn't have an example of stable in here, but if you go back up to the phase portrait, notice that this unstable point was because we were increasing going through the critical point. If you go back to the previous video, we had a critical point where we were decreasing through it, and that meant that this was a stable critical point. So y naught is stable if the derivative of f evaluated at y naught is less than 0, meaning it travels through the critical point heading downward. So if your phase portrait travels through the critical point heading downward, or less than 0 based on the derivative there, it will be a stable critical point. The opposite is true for instability. The critical point is unstable if it's heading in an upward trajectory in the phase portrait through the critical point y naught. And then we just saw in this example when it's semi-stable. So the critical point is semi-stable if the derivative is 0. Notice we had the tangential touch here, so y prime was 0 at that particular point. Or actually, yeah, y prime is 0, which is another way of saying f prime of y naught is 0. So these are the three possible cases. We've got stability if we're traveling down through the point, instability if we're traveling up through the point, and if we just touch the point leading to a multiple root like we had here, y equal to 2 was a repeated root, then that gives us semi-stability. Those are the three possible cases for critical points. All right, hope you enjoyed the video. Thanks for watching.